100 kilometers straight up, an invisible line holds the key to the cosmos. This is the Kármán line, the official boundary where our world ends and outer space begins. It is not a wall or a fence you can see, but a profound scientific and legal frontier with staggering implications for our future. By the end of this journey, you will understand 25 astonishing facts that reveal why this line is one of humanity's most important ideas. We will uncover why the air itself stops working there, how climate change might be making space closer to Earth, and what strange glow permanently hugs our planet at this altitude. So where do you think our planet truly ends? But what makes 100 kilometers so special? This number is not arbitrary, but a profound calculation born from a clash of two fundamental forces. Below this line, the atmosphere is thick enough that wings can generate lift, allowing aircraft to fly. Above it, the air becomes so vanishingly thin that no wing, no matter how advanced, can provide enough upward force. To stay aloft, an object must instead achieve orbital velocity, moving so fast horizontally that as it falls toward Earth, the planet's curvature drops away beneath it at the same rate. This precise tipping point where the physics of flight surrenders to the physics of orbit is the Kármán line. It is a theoretical line of pure mathematics drawn across an empty sky. You could pass through it and feel absolutely nothing, yet you would have crossed a fundamental frontier of human endeavor. Even this official number has its debates. Some organizations, like the United States Air Force, set the boundary at 50 miles or roughly 80 kilometers, awarding astronaut wings to pilots who reach that mark. This slight variation highlights the line's nature as a brilliant, necessary approximation for law and science, a placeholder for the infinite gradient where our blue sky fades into the black ocean of space. The man who gave this cosmic boundary its name was a true titan of the sky. Theodore von Kármán was a Hungarian-American aerospace engineer whose mind seemed to operate on a different plane of reality. A child prodigy in mathematics, he fled the rising turmoil in Europe and brought his genius to the California Institute of Technology. There, he became a central architect of the jet age, pioneering research into supersonic flight and rocketry that would shape the world. In the 1950s, while advising international committees on the nascent laws of space, he was asked a deceptively simple question: where exactly does airspace end and outer space begin? For a legal treaty, they needed a number. Von Kármán approached it not as a lawyer but as a physicist. He calculated the altitude where a vehicle would have to fly so fast to generate aerodynamic lift that it would, in fact, achieve orbital velocity. That elegant calculation, the point where aeronautics ends and astronautics begins, settled at roughly 100 kilometers. It was a perfect fusion of profound theory and practical necessity. His name was immortalized on that line not by decree, but by the sheer weight of his intellectual legacy. Today, every satellite, every space station, and every astronaut who crosses that silent frontier does so by passing through a gateway defined by Theodore von Kármán's brilliant mind. This conceptual nature of the boundary leads us to a crucial truth. The Kármán line is not a hard edge. You will not hit a cosmic pane of glass or see a sudden change in color as you ascend. Think of it instead like the fading of twilight into night. The sun dips below the horizon, but the world does not plunge instantly into darkness. The light lingers, softening and dissolving gradually until you realize at some imperceptible moment that full night has arrived. The atmosphere behaves in exactly this way. It thins out slowly, molecule by molecule, over hundreds of kilometers. At the altitude we call the Kármán line, the air is already a near vacuum, about 1 million times thinner than at sea level. Yet trace wisps of atmosphere persist far higher, gently brushing against the International Space Station and creating a faint, permanent glow around our planet. So why choose 100 kilometers? It is because we, as a species building machines and writing laws, require a clear marker. Just as a society might define adulthood at age 18 for legal purposes, knowing full well maturity is a gradual process, scientists and diplomats needed a practical, physics-based number to answer a critical question. Where does a country's sovereign airspace end, and where does the free, international realm of outer space begin? That number had to be rooted in a fundamental change in the rules of travel, the shift from flying to orbiting. So while the transition is a gentle gradient, the line itself is a brilliant and necessary declaration, a stake driven into the continuum of the sky to say, from here we are no longer merely flying. We are sailing on the orbital sea. This brilliant declaration of a boundary solved a problem far bigger than physics. It created the foundational rulebook for humanity's activities beyond Earth. That rulebook is the Outer Space Treaty of 1967, a document signed at the height of the Cold War that remains the cornerstone of international space law. Its first and most critical principle is that outer space is not subject to national appropriation. No country can claim the moon, a planet, or any celestial body as its own territory. But for this principle to work, everyone first had to agree on where a nation's territory ends. This is the Kármán line's profound legal duty. Below it, the airspace belongs to the sovereign nation beneath it, governed by its laws. The moment a vehicle crosses above 100 kilometers, it enters the province of all humankind. This transforms a satellite from a potential trespasser into a lawful traveler. Every operational satellite, from weather monitors to GPS networks, flies in this free zone, a global commons where no single nation holds sway. This legal clarity is what allows the International Space Station, a partnership of 15 nations, to orbit peacefully. The astronauts and cosmonauts aboard are not under the jurisdiction of the countries they fly over, but operate under the legal framework established by the treaty. They are envoys of humanity, a status defined the instant their spacecraft crossed that invisible 100-kilometer line. This distinction is absolute. A pilot flying a spy plane at 99 kilometers could be shot down as an intruder. An astronaut in a capsule at 101 kilometers is an international traveler, protected by a treaty that views space as a realm for peaceful exploration and benefit for all. That thin, theoretical line is in practice the most important border on our planet, because it is the one we all agreed marks the end of borders forever. This aerodynamic principle is the beating heart of the entire concept. To understand it, we need to think about how two very different things stay above the ground, an airplane and a satellite. An airplane flies because its wings are shaped to slice through the air. As air flows over the curved top of the wing, it speeds up and creates an area of lower pressure above the wing compared to the higher pressure below. This difference, this lift, is what pushes the plane upward, but lift depends entirely on air molecules. The fewer molecules, the less lift you can generate. Now imagine you're piloting a plane straight up, climbing higher and higher. The air gets thinner and thinner. To compensate for the loss of lift, you would have to go faster and faster to force enough air over your wings. This brings us to the critical calculation. Theodore von Kármán determined that at an altitude of roughly 100 kilometers, the air is so incredibly thin that to generate any meaningful aerodynamic lift at all, a conventional aircraft with wings would have to be traveling at an astonishing speed. That speed is approximately 7.8 kilometers per second, which is about 17,500 miles per hour. But here is the cosmic twist. Traveling horizontally at that exact speed is precisely what you need to do to achieve a stable orbit around Earth. At that velocity, as your vehicle is constantly falling toward the planet due to gravity, the Earth's surface curves away beneath it at the same rate. You are in a perpetual state of freefall, which we call orbit. So, at the Kármán line, the physics of flying and the physics of orbiting collide and become the same thing. A traditional aircraft simply cannot exist there. If it tries to fly like a plane, it must go orbital speed, which no propeller or jet engine could ever achieve in that thin air. And if it is going orbital speed, it is no longer flying, it is orbiting, and wings become useless. This is the brilliant, clean break the line represents. It is the altitude where the sky finally runs out of the substance that makes flight possible, forcing any traveler to adopt the entirely different rules of spaceflight. Standing at that precise boundary, the world transforms into a spectacle of impossible contrasts. From 100 kilometers up, you would witness a view that redefines the very idea of a horizon. The curvature of the Earth is unmistakably, breathtakingly apparent. You are not looking at a flat landscape stretching to a distant line, but at a vast blue marble arcing away into the distance. Below you, the planet is a tapestry of land and sea, but the details are softening, the colors blending. You are high enough to see enormous weather systems as swirling patterns, yet not so high that continents become mere outlines. The most striking feature, however, is the thin, luminous band hugging the planet's edge. This is the entirety of our atmosphere, compressed into a fragile, glowing ribbon of blue light against the profound and absolute blackness of space. That black is not like night sky. It is a deep, velvety void, utterly empty and punctuated by stars that do not twinkle but burn with a steady, cold fire. From this vantage, night and day cease to be daily events. In a single 90-minute orbit, you would see the sun rise and set, a blinding star that ignites the atmospheric halo in a flash of colors before vanishing again into the cosmic dark. This is a more transitional perspective than the classic view from the International Space Station, which orbits much higher. From the station, Earth feels like a distant globe, a complete sphere hanging in the void. But from the Kármán line itself, you are poised perfectly at the cusp. You are still intimately connected to the world scale, yet you are staring directly into the infinite. It is the last place from which Earth still feels like a home, and the first place from which it truly looks like a spacecraft. This breathtaking view from the edge comes with a hidden, paradoxical danger. The region where the Kármán line is drawn, known as the thermosphere, is one of the hottest places in Earth's entire vicinity. Temperatures here routinely reach between 1,000 and 2,000 degrees Celsius, and during periods of intense solar activity, they can spike to over 2,500 degrees. That is hotter than the surface of a steel melting furnace. Yet, if you were to find yourself floating at that altitude in a spacesuit, you would not be instantly vaporized. In fact, you would freeze to death. This staggering contradiction is one of the most important facts about the true nature of our cosmic frontier. Heat, as we experience it on Earth, is the transfer of energy through the constant, frantic collisions of molecules. When you touch a hot stove, trillions of air molecules energized by the metal are crashing into your skin. The thermosphere is searingly hot because the few gas molecules that exist there are being bombarded by intense solar radiation, giving them enormous individual energy and speed. However, those molecules are so incredibly far apart, sometimes kilometers between each one, that they almost never collide with each other or with anything else. There is simply not enough matter to transfer that thermal energy to an object like a satellite or an astronaut. A spacecraft in orbit does not feel that 1,000-degree heat because it is surrounded by what is essentially a super-energetic vacuum. The real thermal challenge for these machines comes from direct, unfiltered sunlight on one side and the deep freeze of shadow on the other, a brutal cycle that engineers must carefully manage. So the Kármán line exists within a realm of extreme temperature that is simultaneously a profound cold. It is a place where the very definitions of hot and cold are rewritten by the emptiness between the stars. The paradox of heat without warmth is a perfect introduction to the strange new rules that govern life above the line. To truly appreciate this shift, we can contrast it with another legendary frontier of flight, the sound barrier. Both were once considered impossible walls, but their nature could not be more different. Breaking the sound barrier was a triumph of engineering over a physical phenomenon within our atmosphere. As an aircraft approaches the speed of sound, air molecules cannot get out of the way fast enough, piling up into a wall of compressed air that creates immense drag and violent shock waves. The challenge was to build a machine strong enough and shaped precisely enough to punch through that turbulent wall of air itself. When Chuck Yeager piloted the Bell X-1 through Mach 1 in 1947, he proved that with enough power and the right design, we could master the thick, resistant medium we call the sky. Crossing the Kármán line, however, is not about overcoming a barrier within a medium. It is about leaving the medium behind entirely. It is the transition from a realm where you push against something to a realm where there is almost nothing to push against at all. The challenge shifts from brute force aerodynamics to the delicate orbital ballet of celestial mechanics. Yuri Gagarin's journey in 1961 was not about piercing a wall, but about achieving a precise, fragile equilibrium with gravity itself. His Vostok 1 capsule did not blast its way into space so much as it ascended to an altitude where it could be set adrift on an invisible track carved by physics. One milestone was about conquering the air's resistance, the other about escaping its embrace to enter the silent, frictionless ocean of space. The sonic boom announces a victory over the sky. The crossing of the Kármán line is a quiet entry into a new and infinite world. This dramatic difference in purpose brings us to a vital distinction in modern spaceflight. Crossing the Kármán line is an incredible achievement, but it is not the final goal for most missions. The critical split is between a suborbital hop and achieving true orbit, and the gap between them is not just one of altitude but of pure, raw velocity. Think of it this way. A suborbital flight, like those conducted by Virgin Galactic, is like a spectacular leap over a puddle. The vehicle rockets straight up on a towering arc, crosses the 100-kilometer line for a few minutes of weightlessness, and then curves gracefully back down to land. It is a breathtaking vertical sprint that gives passengers a stunning view and a taste of zero gravity, but it does not have the sideways speed to stay in space. The entire flight from launch to landing might last just over an hour. Achieving orbit, as done by SpaceX's Falcon 9 or Russia's Soyuz rockets, is an entirely different kind of endeavor. It is not about jumping over the puddle, but about running so fast along its edge that you can circle the entire globe without ever falling in. To do this, a spacecraft must do two things. First, it must climb vertically to get above the thick atmosphere, just like the suborbital vehicle. But second, and most crucially, it must then pivot and accelerate sideways with unimaginable force. It must reach that orbital velocity of about 28,000 kilometers per hour. At that speed, the spacecraft's forward momentum perfectly balances the pull of Earth's gravity, creating that perpetual state of freefall we call an orbit. The energy required for this horizontal acceleration is staggering. Roughly 80 to 90% of a rocket's fuel is spent not on going up, but on achieving this incredible sideways speed. This is why a suborbital tourist flight and launching a satellite or crew to the International Space Station are worlds apart in complexity, cost, and capability. One is a magnificent vertical arc to the edge of space, a brief kiss with the void. The other is a violent, precise sideways throw that grants a permanent seat in the cosmic ballet, allowing an object to circle our planet for years. Both cross the Kármán line, but only one truly unlocks the door to the solar system. This crucial distinction between a hop and a permanent seat raises an important question. Who gets to decide what officially counts as space? For the answer, we must turn to the world's official record keeper for flight, the Fédération Aéronautique Internationale, or FAI. Founded in 1905, this international body is the authority that certifies everything from the first solo flight around the world to the highest altitude reached by a balloon. When the space age dawned, they faced a new challenge. They needed a clear, universal standard to determine who had earned the title of astronaut. After careful consideration, they formally adopted the Kármán line at 100 kilometers as that definitive boundary. To receive the FRI's internationally recognized astronaut wings, a pilot must cross this line in a vehicle they have controlled for at least part of the journey. This decision, however, was not met with universal agreement. It created a quiet but persistent controversy centered largely across the Atlantic. For decades, the United States Air Force and NASA have used a different standard, awarding their own astronaut wings to pilots and mission specialists who reach an altitude of 50 miles, which is approximately 80 kilometers. This lower boundary has historical roots in early high-altitude research and was the benchmark used for the X-15 rocket plane flights in the 1960s. The discrepancy means that several American pilots celebrated as astronauts at home are not recognized as such by the international governing body. This is not merely a bureaucratic debate over a patch. It underscores a fundamental truth about the Kármán line itself. It is a brilliant physics-based concept, but its application as a hard legal and ceremonial line involves a degree of human choice. The 20-kilometer gap between the two standards represents the fuzzy twilight zone of our atmosphere, a region where the physics of flight is dying but not yet completely gone. So, while science gave us the elegant theory of 100 kilometers, politics, history, and national pride have colored its practical application, leaving us with two different answers to the simple question, where does space begin? This split in official recognition leads us directly to the men who first tested these lower skies. The 50-mile line is not just an arbitrary number, it is a line written in the vapor trails of the X-15 rocket plane. In the 1960s, this needle-nosed aircraft, dropped from the wing of a B-52 bomber, was the most advanced machine on the planet. Pilots like Joseph Walker, Robert White, and William Knight would ignite its rocket engine and scream upward on a steep, ballistic arc, pushing the very edges of the atmosphere. The goal was not to orbit, but to explore the extreme frontier of flight, gathering data on hypersonic speeds and re-entry that would prove vital for the coming space shuttle. On multiple flights, these pilots soared past 50 miles, reaching altitudes as high as 67 miles. According to the U.S. Air Force's own standard, they had entered space. They returned to Earth as astronauts, receiving military astronaut wings, even though by the international FI standard, they had stopped just short of the Kármán line. The X-15 program stands as a monumental achievement, a bridge between aviation and astronautics. It proved that a winged vehicle could leave the sensible atmosphere and return to a controlled runway landing. Yet, it also cemented the legitimacy of the 50-mile boundary within American space culture. For NASA and the Air Force, these flights were not suborbital tourism. They were critical, controlled research missions at the absolute limit of the flyable realm. Awarding astronaut wings for crossing 50 miles was a way to honor that unique, perilous work in a zone where the sky itself was giving out. So the debate over the true boundary is not merely academic. It is rooted in the legacy of real pilots who risked everything in that thin, high air, and in the question of whether their incredible journeys should be counted as spaceflight. That legacy of human definition now faces a startling new possibility. The Kármán line itself may not be fixed in place. Recent scientific research suggests this cosmic boundary could be slowly, imperceptibly drifting closer to Earth. The cause is not some shift in the laws of physics, but a profound change happening right here on our planet, a human-driven climate change. It all comes down to the behavior of carbon dioxide, the same greenhouse gas warming our surface. In the incredibly thin air of the upper atmosphere where the Kármán line is drawn, carbon dioxide molecules act in a counterintuitive way. Instead of trapping heat, they actually help radiate it away into space. As we pump more carbon dioxide into the atmosphere, the concentration of this efficient coolant increases in the high altitudes. This causes a gradual but measurable cooling and contracting of the upper atmospheric layers. Think of it like a gentle global sigh. The entire envelope of air surrounding our planet is slowly settling downward as it cools. One influential study calculated that this contraction could be lowering the effective altitude of the Kármán line by several dozen meters every decade. It is a minuscule shift on a cosmic scale, far too small for any spacecraft to notice. Yet the implication is staggering. The most important boundary humanity has ever drawn, the line that separates our world from the cosmos, is not a permanent fixture of our solar system. It is a dynamic feature subtly tied to the environmental health of the planet it encircles. The altitude where aerodynamics fails is being rewritten meter by meter by the collective actions of civilization below. This means the very definition of where space begins is, in a very real sense, a moving target, one that quietly responds to the changing composition of the air we breathe. The idea of a shifting frontier leads us to a crucial and practical reality for everything we place above it. That whisper-thin atmosphere at the Kármán line and for hundreds of kilometers above it is not a perfect vacuum. It is the beginning of a gentle but relentless pull, the cosmic sink that eventually reclaims our machines. This is the dominant force governing the lifespan of satellites in low Earth orbit, the bustling highway just a few hundred kilometers above our heads. Even at these incredible altitudes, stray atoms and molecules of gas still exist, and they exert a force called atmospheric drag. Imagine driving a car with your hand out the window. You feel the push of the air against your palm. A satellite experiences a similar, unimaginably faint pressure from the wisps of atmosphere it encounters. With each pass, this microscopic drag steals a tiny, almost imperceptible amount of the satellite's speed. Since orbital velocity is a precise balance, losing even a little bit of speed is catastrophic for that balance. The satellite begins to dip into a slightly lower, slightly denser part of the atmosphere. Here, the drag increases, slowing it down further, causing it to dip even lower. This creates a feedback loop of decay. Without periodic boosts from onboard thrusters to regain altitude, the satellite's orbit will inevitably decay. It spirals lower and lower until it finally plunges into the thick lower atmosphere, where friction heats it to a fiery incandescence. This is why the International Space Station, orbiting at about 400 kilometers, must regularly fire its engines to nudge itself back up, fighting against this constant, invisible tug. The Kármán line marks the altitude where this sinking process truly begins. It is not a wall keeping things out, but the top of a gradual slope back to Earth. Every satellite we launch is, from the moment it crosses that line, engaged in a slow-motion fall. Its operational life is a race against this gentle, atmospheric breath that will one day bring it home in a final, brilliant streak of light. This slow, inevitable fall means the zone around the Kármán line has become a cosmic graveyard. It is the final resting place for countless spacecraft, a silent junkyard where humanity's orbital ambitions are quietly incinerated. Every satellite that runs out of fuel, every spent rocket stage discarded during launch, and every forgotten tool dropped by an astronaut is destined for this fate. They do not remain in orbit forever. Dragged lower by that faint atmospheric breath, their orbits decay until they finally dip into the thicker air near and below the 100-kilometer mark. This is where the vacuum of space truly ends and our planet's protective shell begins to bite back. An object re-entering at orbital velocity is moving so fast that it compresses the air in front of it violently, creating a blistering plasma of superheated gas. Temperatures can exceed 1,600 degrees Celsius, hot enough to vaporize aluminum and steel. For most spacecraft, especially smaller ones or those not built to survive, this is a complete and fiery disintegration. The vast majority of orbital debris simply burns up into harmless dust and tiny fragments that rain down imperceptibly across the globe. This atmospheric interface acts as our planet's built-in cleaning system, a protective incinerator that constantly purges the lower orbits of our celestial clutter. We have witnessed some spectacular re-entries, like the deliberate, controlled plunge of the Russian space station Mir in 2001, which was steered into the South Pacific, or the unexpected, glowing debris trail of a Chinese rocket stage over the Indian Ocean. These events remind us that everything we send up must eventually come down, and the Kármán line marks the threshold where that fiery descent begins in earnest. This reality has made controlled deorbiting a critical part of modern spaceflight ethics. Instead of letting a dead satellite tumble unpredictably for decades, responsible operators now use their last fuel reserves to guide it into a precise re-entry corridor over a vast, unpopulated ocean. It is a final act of stewardship, ensuring that our frontier above the line does not become permanently littered with hazards, and that what must return does so safely, leaving only a brief, brilliant streak in the night sky as its memorial. That protective incinerator of re-entry operates in a layer that also hosts one of our planet's most breathtaking spectacles. The same thin, energetic gases that slowly drag satellites down also paint the sky with ethereal light. The dancing curtains of the Aurora Borealis and Aurora Australis are in essence space weather made visible, and their celestial canvas stretches right down to the realm of the Kármán line. While the most intense displays typically shimmer between 80 and 400 kilometers in altitude, their uppermost tendrils can indeed brush against that 100-kilometer frontier. This means that if you were theoretically positioned right at the boundary of space, looking back toward Earth's poles, you might see the ghostly tops of these luminous rivers flowing beneath your feet. The creation of an aurora is a direct conversation between the sun and our upper atmosphere. The sun constantly exhales a stream of charged particles called the solar wind. During periods of heightened solar activity, like flares or coronal mass ejections, this wind becomes a storm. When these energized particles are funneled by Earth's magnetic field toward the poles, they slam into the sparse gases of the thermosphere, the very layer that contains the Kármán line. The collisions excite oxygen and nitrogen atoms, making them glow in brilliant hues of green, red, and purple. So the thin, superheated gas that defines our cosmic boundary is also the phosphorescent paint for these heavenly displays. The Kármán line is not just a passive altitude marker, it is part of an active and dynamic interface. It sits within the zone where the raw energy of the sun physically touches and illuminates the last vestiges of our air, transforming the frontier of space into a theater of sublime beauty. The fiery glow of re-entry and the shimmering auroras highlight a crucial truth. The Kármán line exists within a specific, dynamic neighborhood of our sky. To understand its true significance, we must see it not as a solitary fence, but as a landmark within the grand, layered structure of Earth's atmosphere. That structure is defined by temperature, and the Kármán line sits firmly within a layer called the thermosphere, the realm of extreme heat without warmth we discussed earlier. This is the atmospheric layer that begins about 80 kilometers up and extends outward for hundreds more. Above the thermosphere, however, lies the final, most ethereal layer of all, the exosphere. This is the true fringe of our planet's influence, a zone so thin it barely qualifies as an atmosphere at all. Here, gas particles are so incredibly sparse that they can travel for hundreds of kilometers without colliding with another. They move more like individual satellites than part of a cohesive gas. This is the realm where the very concept of an atmosphere dissolves. Atoms and molecules in the exosphere, if they are moving fast enough and on the right trajectory, can simply escape Earth's gravity altogether, sailing off into the interplanetary medium. This slow, constant leakage is how our planet has been losing its lightest elements, like hydrogen and helium, over billions of years. So, if the exosphere is where Earth's grip finally fails, where does the Kármán line fit in? It sits well below this ultimate frontier, The line at 100 kilometers is not where the atmosphere ends, but where human practicality demanded a clear, physics-based starting point for space. It is a bright, bold line we drew in the middle of a very long, very gradual fade-out, from the thick air of the ground through the thinning thermosphere where satellites face drag, past our defined boundary, and out through the vast, ghostly exosphere. The transition from Earth to space is a journey of thousands of kilometers. The Kármán line is our way of planting a flag at the moment the rules of travel fundamentally change, a human milestone on the endless road to the stars. This gradual fade from Earth's embrace has now become the ultimate destination for a new kind of traveler. The commercial space race has set its sights squarely on the Kármán line, transforming a theoretical physics boundary into a trophy for private adventure. Companies like Virgin Galactic are not aiming for orbit, but for that precise 100-kilometer mark, because crossing it carries a powerful, almost mythical status. It is the definitive threshold that separates an extreme airplane ride from a genuine spaceflight. Their vehicle, Spaceship Two, is designed for a suborbital arc. Carried aloft by a mothership, it then fires its rocket motor, shooting nearly straight up on a steep climb. For a few precious minutes, passengers unbuckle and float in weightlessness as they soar past the line. The experience is brief but meticulously crafted. They have a minute to scramble out of their seats, experience the surreal freedom of zero gravity, and press their faces against the large windows to behold the curvature of the planet against the blackness of space. This is the core product, and its entire value hinges on that crossing. Virgin Galactic does not sell a high-altitude flight, it sells the moment you become an astronaut. Their marketing, their certification with the FAI, and their very identity are built upon delivering customers to that invisible frontier. The ticket, costing hundreds of thousands of dollars, purchases a transformation. You board the vehicle as a civilian, but you cross the Kármán line as a private astronaut, joining an elite group who have witnessed our world from the outside. This commercial targeting has cemented the line's role in popular culture, no longer just a tool for scientists and lawyers, but a finish line for human aspiration, a dream now available for purchase. That ticket to cross the cosmic frontier carries an astronomical price tag, and the reason is written in the unforgiving mathematics of energy. Reaching the Kármán line demands a staggering amount of power, but achieving orbit requires something exponentially greater. To understand this, we need to follow the fuel. For a suborbital hop like the one Virgin Galactic offers, the vehicle essentially makes a powerful vertical sprint. It needs enough thrust to push through the thickening atmosphere and climb to 100 kilometers against Earth's gravity, but it does not need to achieve the impossible sideways speed for orbit. This allows for a fundamentally different and less expensive vehicle design. Spaceship Two is air-launched from a carrier aircraft, which gives it a free ride to about 15 kilometers, saving a huge amount of fuel from the start. Its rocket motor then fires for roughly 1 minute, providing the kick to ascend and cross the line before it coasts back down. The entire propulsion system is simpler, smaller, and the vehicle can be largely reusable, which is key to controlling costs. The price for this experience is currently around $450,000 per seat. Now, compare this to buying a ride to orbit. SpaceX's Falcon 9 rocket, for instance, must accomplish that suborbital climb and then perform the critical fuel-guzzling pivot to accelerate sideways to 28,000 kilometers per hour. The energy required for that horizontal acceleration is monstrous. The rocket must carry not only the fuel to lift its own weight, but also the fuel to lift the weight of all the fuel it will burn later in the flight. This is why rockets appear to be mostly giant fuel tanks with a small payload on top. A seat on a SpaceX Crew Dragon mission to the International Space Station, brokered through a company like Axiom Space, costs in the realm of $55 million per astronaut. That is over 100 times more expensive than the suborbital ticket. The difference is the price of velocity. The suborbital flight buys you altitude, a view, and a few minutes of weightlessness. The orbital flight buys you the entire cosmic racetrack, the perpetual fall that lets you circle the planet every 90 minutes, a perspective reserved for those who have truly broken the bonds of Earth. One is a magnificent leap to the edge, the other is the purchase of a permanent key to the kingdom of space. This immense cost for a ticket to orbit underscores just how precious a resource that cosmic frontier has become. Yet long before we could price it, we dreamed it. The Kármán line has transcended its scientific origins to become a powerful symbol in the stories we tell ourselves about the future. In science fiction, this invisible boundary is often the ultimate gate, the moment a story shifts from being about our world to being about the infinite. The film Gravity provides a perfect, terrifying example. The entire narrative hinges on the catastrophic aftermath of crossing that line. When debris destroys the space shuttle, astronauts Ryan Stone and Matt Kowalski are not just stranded in space, they are stranded above the Kármán line, in a realm where the simple act of breathing or taking a single step is an impossible engineering miracle. The line is the prison wall. Every desperate attempt to reach the International Space Station or a Chinese space capsule is a struggle to find a way back down through that lethal interface. The film visually reinforces this, contrasting the serene, postcard view of Earth with the utter hostility of the vacuum just outside the window. The Kármán line is the unspoken rule that makes their predicament so dire. It is the reason a short distance of a few hundred kilometers might as well be a million light years. Other stories use the crossing as a moment of profound transformation. In the television series The Expanse, the political and cultural divide between Earth, Mars, and the Belt is often framed by who controls travel through this orbital space. Crossing the line is not just a technical maneuver, it is a passage into a different human condition, one defined by different physics, different dangers, and a different relationship to the planet below. This narrative power works because the line represents a fundamental truth we all intuitively understand. It separates the known from the unknown, the safe from the lethal, the home from the wilderness. By embedding this real scientific concept into fiction, storytellers ground their cosmic adventures in a reality we can grasp. We watch a character cross that threshold and we feel the stakes instantly elevate because we know, on some level, they have left behind every safety net our world provides. The Kármán line, in our collective imagination, is where fairy tales end and epic myths begin. That symbolic power of the crossing is not just for individuals or corporations, it is a defining moment for entire nations. For a country, successfully launching a payload past the Kármán line is a rite of passage, a declaration to the world that it has arrived as a technological and strategic power. It marks entry into an elite club far more exclusive than the nuclear club, the spacefaring club. The first members were, of course, the superpowers of the Cold War. The Soviet Union with Sputnik in 1957 and the United States with Explorer 1 in 1958 did not just launch satellites, they launched a new era of geopolitics. But the true weight of this milestone is felt most profoundly by the nations that followed. Consider Japan. In 1970, it became the fourth country to achieve an orbital launch with its Lambda 4S rocket carrying the Asumi satellite. That successful crossing was a national triumph, a symbol of Japan's post-war recovery and its emergence as a leader in precision engineering. For the European Space Agency, the successful Ariane 1 launch in 1979 was a statement of continental independence, proving Europe did not need to rely on American or Soviet rockets to access the cosmos. Each new member of this club writes its name with fire and physics. India's Polar satellite launch vehicle, China's Long March rockets, Israel's Shavat launcher, each maiden orbital flight was a moment of intense national pride, broadcast live and celebrated as a historic achievement. It signals that a country possesses the complex ecosystem of advanced materials science, software engineering, guidance systems, and massive logistical coordination required for such a feat. More than a scientific project, it is a national project uniting thousands of engineers and capturing the imagination of millions of citizens. The payload itself is almost secondary, whether it is a simple test satellite or a lunar probe. The primary objective is to prove that the country can, on its own terms, cross that invisible line and claim its place in the final frontier. This national pride in reaching orbit has created an unintended and perilous legacy. Just above the Kármán line, in the bustling orbital lanes of low Earth orbit, a silent storm is brewing. We have not just visited this frontier, we have moved in and we have left our trash everywhere. This region, starting from about 160 kilometers up, is now cluttered with a cloud of human-made debris. It is a junkyard of epic proportions, filled with defunct satellites that have run out of fuel, spent rocket stages discarded during launch, and countless fragments from explosions, collisions, and anti-satellite weapon tests. A stray bolt, a chip of paint, even a frozen droplet of coolant, all of it is still up there, traveling at orbital speeds of around 28,000 kilometers per hour. At that velocity, a paint fleck carries the kinetic punch of a rifle bullet. A metal screw becomes a cannonball. This is the reality of the space debris problem, a danger that begins the moment we cross the cosmic boundary and one that grows with every new launch. The ultimate nightmare scenario for this crowded frontier has a name: Kessler syndrome. Proposed by NASA scientist Donald Kessler in the 1970s, it is a chain reaction of destruction. Imagine one major collision between two derelict satellites. That impact does not just destroy two objects, it shatters them into thousands of new fragments, each a new high-speed projectile. These fragments then spread through the orbital lanes, dramatically increasing the probability of hitting other satellites, which then create more debris in a cascading explosion of shrapnel. One collision could trigger another, and then another, until a dense cloud of debris forms, making certain orbits so hazardous that they become impassable. Satellites for weather forecasting, global communications, and GPS navigation could be shredded. The International Space Station would face constant, unacceptable risk, forcing its evacuation. New rockets would struggle to find a safe path through the minefield to reach higher orbits. In a severe Kessler syndrome event, entire bands of space around our planet could be locked away from us for generations, the shrapnel moving too fast and too unpredictably to clean up with current technology. We will be trapped on Earth by a shell of our own making. Managing this growing debris field is now one of the most critical challenges for our future in space. It is a problem of both cleanup and prevention. For prevention, modern guidelines now require satellite operators to plan for a responsible end of life. This means reserving enough fuel to either push a dead satellite into a much lower orbit where it will quickly burn up, or sending it farther out into a designated graveyard orbit away from the busy zones. New satellites are also being designed to be more resilient, with fewer parts that can break off. The real difficulty, however, lies in cleaning up the debris already there. How do you catch a spinning, tumbling rocket stage the size of a school bus that is moving 10 times faster than a bullet? Concepts are being tested, from robotic arms and nets to harpoons and even lasers that could nudge debris into a decaying orbit. The first dedicated debris removal missions are now in active development by space agencies and private companies. Their success or failure will determine whether the highway just above the Kármán line remains open for business or becomes a celestial dead end, a monument to our carelessness at the very threshold of the stars. But the view from that crowded frontier holds a secret light, one that has nothing to do with our cities or our machines. High above, where the atmosphere whispers into nothingness, our planet perpetually wears a crown of soft, ethereal light. This is airglow, a permanent, faint luminescence that bathes the entire Earth in a ghostly shroud, and its home is the very layer that contains the Kármán line. Unlike the dramatic, dancing curtains of the auroras, which are confined to polar regions, airglow is a global phenomenon. It is a gentle, all-encompassing veil of light caused by the atmosphere itself, constantly breathing out photons. The process begins with the sun's relentless barrage of ultraviolet radiation. This high-energy light smashes into the sparse molecules in the upper atmosphere, the thermosphere and mesosphere, tearing electrons from their atoms. Later, when these atoms and molecules recombine or settle back into a calm state, they release that stored energy as a faint, colorful glow. Different gases produce different hues. Oxygen gives off a deep red or a greenish yellow, while sodium from micrometeorites burning up contributes a soft orange. From the ground, this glow is almost always invisible, drowned out by moonlight, light pollution, or even the bright stars. But for an astronaut gazing out the window of the International Space Station, airglow is an unforgettable sight. They see it as a thin, luminous band hugging the curve of the Earth, separating the blackness of space from the darkness of the night side of the planet below. It is not the sharp, electric glow of city lights, which appear as distinct clustered specks, nor is it the vibrant, moving ribbons of the auroras. Airglow is smoother, more diffuse, a constant and serene halo that reminds us our atmosphere is not just empty space, but a dynamic, chemically active entity, forever painting the edge of our world with its own quiet light. This permanent, gentle glow of airglow is a reminder of our planet's vibrant, protective shell, a shell that defines the very possibility of life, and that brings us to a profound biological truth. The Kármán line is more than a legal or physical boundary. It is the ultimate ecological frontier, the absolute ceiling for life as we know it. No organism native to Earth can naturally survive, let alone reproduce, in the permanent environment above this line. It is the hard edge of our planet's biosphere. Think of the most extreme extremophiles on Earth. The resilient tardigrade or water bear can endure incredible hardships. It can be frozen to near absolute zero, boiled, crushed under immense pressure, and even survive the vacuum of space for short periods in a dormant state. But its survival is a temporary pause, a desperate hibernation. It cannot actively live, metabolize, or reproduce in that void. Above the Kármán line, the conditions are not just harsh, they are utterly alien. First, there is the vacuum. This is not simply a lack of air to breathe. It causes the violent boiling of bodily fluids at room temperature and the rapid expansion of gases trapped within tissues. An exposed organism would essentially desiccate and rupture from the inside out. Then there is the radiation. Below the line, our thick atmosphere and magnetic field act as a colossal shield, deflecting and absorbing the sun's deadly cosmic rays and ultraviolet radiation. Cross that line and you step directly into that unfiltered stellar barrage. This radiation shreds DNA, destroys cellular structures, and would lead to rapid death for any complex life. Finally, there are the temperature extremes, swinging hundreds of degrees between sunlight and shadow, and the complete absence of pressure, water, and nutrients. Life on Earth evolved within a protective bubble, a delicate cradle of air, water, and magnetic protection. The Kármán line marks where that cradle ends. Every bird, every insect, every seed carried by the wind, every microbe swept into the upper atmosphere, all meet their absolute limit here. This makes the line a biological cliff face. It is the altitude beyond which Earth's evolutionary experiment cannot venture without the artificial, sealed environment of a spacecraft or suit. In a very real sense, when we cross that line, we are not just leaving our country or our atmosphere behind, we are leaving the entire living world. We are stepping out of the only environment that has ever nurtured life, into a realm that is, by its very nature, sterile and lethal to it. This transforms the Kármán line from an engineering milestone into something almost sacred, the final border of our shared garden, a silent memorial to the fragility and preciousness of the thin, glowing band that makes our world alive. This absolute limit of life is the very reason we build machines to cross it. Those machines, our spacecraft, rely on the Kármán line as a silent but essential guidepost in the void. While it is not a physical wall, it serves as a critical navigational landmark for every mission that leaves our planet. Engineers and flight controllers use this conceptual boundary as a universal reference point for the most dangerous phases of a journey, launch and re-entry. During ascent, a rocket is not just climbing, it is fighting through an atmospheric soup that creates immense drag and stress. Mission profiles are carefully calculated to punch through the thickest part of this soup as efficiently as possible, with the understanding that once they pass approximately 100 kilometers, the rules change. The atmosphere's grip becomes negligible, and the vehicle can focus entirely on the pure orbital mechanics of achieving the correct speed and trajectory. This transition is not left to chance. Flight computers are programmed with the expected conditions at that altitude, and engineers use the line as a benchmark to plan critical engine burns, knowing that above it, they are operating in the clean, predictable environment of space. The line's role becomes even more crucial on the way home. Re-entry is a controlled catastrophe, a high-stakes maneuver where a spacecraft must shed its enormous orbital velocity by plunging back into the atmosphere. They cannot come in too steeply or they will burn up from the intense friction. They cannot come in too shallowly or they will skip off the atmosphere like a stone on a pond, bouncing back into space. The target for this precise, fiery dive is called the entry interface, and it is almost always defined as the moment the spacecraft reaches an altitude of 120 kilometers. Why that number? Because it is just above the Kármán line. Engineers use our defined boundary as the anchor for this calculation, knowing that below it, the atmosphere will be dense enough to begin the vital process of aerodynamic braking. The spacecraft's heat shield is designed to withstand the plasma generated at these specific altitudes and velocities. So, when a capsule like SpaceX's Dragon or Russia's Soyuz is coming home, its computers are not looking for a visual marker. They are tracking altitude and velocity, waiting for the moment they cross that invisible threshold where the equations of orbital flight must give way to the brutal physics of atmospheric re-entry. The Kármán line is the switch that tells the vehicle, the freefall is over, now you must fly, or rather, fall with purpose, using the last vestiges of our planet's air to slow your meteoric descent. It is the starting gun for the final, breathless race to a safe landing. That invisible line drawn at 100 kilometers is ultimately a mirror, reflecting not a physical truth of the universe, but a profound truth about ourselves. This final fact is perhaps the most significant of all, the philosophical weight of the Kármán line. It represents humanity's bold and necessary act of drawing a box around the infinite. We are a species that needs definitions, that requires landmarks to navigate not just geography, but concepts. We looked up at the seamless gradient from blue sky to black space and declared, here, right here, is where it changes. In doing so, we did something uniquely human. We created a shared story about our place in the cosmos. The line marks our collective transition from earthbound creatures, subjects of a single world's gravity and weather, to spacefaring beings, citizens of a solar system. It is a symbol of our technological triumph, yes, a testament to the mathematics and metallurgy that can lift us beyond our cradle. But more deeply, it is a symbol of an innate, unstoppable desire. The same urge that pushed ancient explorers to map coastlines and cross oceans now pushes us to map this new, vertical frontier. The Kármán line is the current shoreline of human exploration, the edge of the map where we once wrote, "Here be dragons," and now we go to meet them. It is useful to think of it alongside another famous human invention, the prime meridian at 0 degrees longitude in Greenwich. That line is an absolute fiction, a complete abstraction. There is no natural feature on Earth that designates Greenwich as the center of global time and navigation. We all simply agreed upon it, and by that agreement it became real, enabling global trade, travel, and communication. The Kármán line is the prime meridian of the sky. It is a brilliant fiction made real by international consensus and the laws of physics. We agreed that 100 kilometers is where space begins, and because we agreed, it became the rule that organizes our satellites, our astronauts, our laws, and our dreams. It is a line that contains our ambition, giving shape to the formless void so we can begin to build within it. So, when you look up at the night sky, remember that the most important boundary between here and there is not a wall placed by nature, but a gateway built by human curiosity. It is our declaration that the unknown is not a barrier, but a destination. That line we drew in the sky is a story of human audacity, told in 25 astonishing chapters. It is a legal border that ends national territory, a physical frontier where wings become useless, and a symbolic gateway that transforms a pilot into an astronaut. This invisible boundary dictates the fiery fate of our satellites, cradles the ghostly light of airglow, and may even be drifting closer to Earth because of the changes we are making far below. It is where our atmosphere's protective embrace finally fails, leaving life utterly exposed to the vacuum and radiation of the cosmos. Yet it is also the landmark we navigate by, the starting gun for every safe return home. The Kármán line is not a discovery of nature, but a declaration of intent. It is our way of saying the infinite gradient from blue to black is not a barrier to be feared, but a shoreline to be crossed. We have touched that shoreline, first with probes, then with people, and now with private dreams. Each crossing reaffirms a simple, profound truth. We are a species that cannot help but reach beyond the edge of the map. So, which of these 25 facts reshaped your understanding of where our world ends? Was it the moving line, the cosmic graveyard, or the silent glow that forever hugs our planet? Share your thoughts below, and if you want to explore more mysteries hidden just beyond our atmosphere, be sure to subscribe for our next deep dive into the secrets of space.